Imagine measuring the reaction time of 1,000 people. You would not get one answer. You would get a cloud of answers. Many near the middle, fewer far away. Stack those measurements into narrow bins, and a hill begins to appear. Smooth the top of that hill, and you get the famous bell curve. That curve is called a normal distribution. But here is the important part. Normal does not mean ordinary, healthy, or required. It is a mathematical model for one particular pattern of variation. In this video, we will build that pattern visually, then learn exactly what it says and what it definitely does not say. Start with the raw measurements. Each dot is one person. A dot by itself is just a value. Now group nearby values and count how many land in each group. The bars form a histogram. With more people and narrower groups, the outline becomes smoother. The smooth curve is not floating above the data as decoration. It is a compact description of where values tend to concentrate. High parts mean values nearby are common. Low parts mean values nearby are rare. A normal distribution is this idealized, perfectly smooth, symmetric version of the hill. Real data remain dots. The distribution is the model we use to reason about those dots. The first control is the center. For a normal distribution, the center is labeled mu, the Greek letter for the mean. Imagine every reaction time becoming 20 milliseconds slower. The entire hill slides to the right, but its shape does not change. If every value became 20 milliseconds faster, the hill would slide left. Mu tells us where the balance point sits on the number line. Because the normal curve is symmetric, its mean, median, and most likely region all meet at the center. Changing mu changes location, not width. One parameter moves the whole pattern without stretching it. The second control is spread. It is labeled sigma, the standard deviation. When sigma is small, measurements cluster tightly around the mean. The curve becomes narrow and tall. When sigma is large, measurements are more varied. The curve becomes wide and low. Notice the trade-off. Spreading the same total probability across more space forces the peak downward. Sigma has the same units as the measurement, so a sigma of 15 milliseconds describes a typical scale of distance from the mean. Mu answers, where is the hill? Sigma answers, how wide is the hill? Together, those two numbers determine the entire normal curve. Now forget the peak for a moment and look at area. The entire area under a probability curve equals 100%. To ask for the chance of landing between two values, shade the region between them. The shaded area is the probability. This is why the height at a single point is not itself a percentage. Height is density, probability packed into nearby space. A narrow interval beneath a tall part may contain useful probability. An interval with zero width contains none, so the curve is best read like a landscape of probability. Choose a horizontal range, then measure the area above that range and below the curve. The normal curve has a memorable geometry. Begin one standard deviation on either side of the mean. The area in that central band is about 68%. Expand to two standard deviations, and the area grows to about 95%. Expand to 3, and it reaches about 99.7%. This is the 68, 95, 99.7 rule. It turns sigma into an intuitive ruler. 1 sigma is the busy center. 2 sigmas include almost everything you would usually expect. 3 sigmas leave only 0.3% in the two outer tails combined. These are approximations, but remarkably useful ones. Suppose one reaction time is 50 milliseconds above the mean. Is that unusual? The raw distance alone cannot tell us. 50 is large when sigma is 10, but modest when sigma is 40. A z-score fixes this by measuring distance in standard deviations. Subtract the mean, then divide by sigma. If the result is +2, the value lies 2 sigmas above the mean. If it is -1, the value lies 1 sigma below. Z-scores let us compare different scales with the same ruler. Only after this picture is clear do we need the formula, z equals x minus mu divided by sigma. Here is the full formula for the normal density. It can look intimidating, but every visible part already has a job. Mu sits inside the distance from the center. Sigma controls how quickly the curve shrinks as we move away. and also adjust the peak so the total area stays 1. The exponential creates the smooth, rapid fall toward both tails. The square makes equal left and right distances behave the same, which produces symmetry. The formula is not the starting idea. It is a precise machine for drawing the picture we already understand. One center, one scale of spread, symmetric decay, and total area equal to 1. Why does this shape appear so often? One major reason is averaging. Imagine a single delivery time that is strongly skewed. Most deliveries are quick, but a few take much longer. Now repeatedly choose several deliveries and compute their average. The averages vary less than individual deliveries, and their histogram becomes more symmetric. Use larger groups, and the hill often moves closer to a normal curve. This is the central limit theorem. Under broad conditions, sums or averages of many independent contributions become approximately normal, even when the original values are not. The theorem explains many bell curves, but it does not declare every dataset normal. Here are 3 shapes the normal model can miss. Income is often right-skewed. A long upper tail breaks symmetry. A mixture of 2 groups can have 2 peaks, hiding important subpopulations behind one average. Some processes have heavy tails, producing extreme values more often than a normal curve predicts. Calling all of these normal would erase structure. A histogram can also look roughly bell-shaped with too little data, so appearance alone is not proof. Before using a normal model, ask, is the shape reasonably symmetric? Is there one main cluster? Are the tails plausible? And is there a real mechanism, such as many small contributions or an average, that supports the approximation? A normal curve never actually touches 0. Its tails extend forever. That means extremely distant values are possible, just increasingly unlikely. So an outlier does not automatically prove that the model is wrong. The useful question is how surprising the value is under the model. A 0.4 sigmas from the mean is very rare for one observation, but in a dataset with millions of observations, rare events eventually show up. On the other hand, many extreme points can signal heavy tails, a measurement problem, or a mixture of groups. The normal model gives a baseline for surprise. It does not give permission to delete inconvenient data. There is one subtle idea worth keeping. Reaction time is treated as continuous. Between 2 displayed numbers, we can imagine more decimal places. For a continuous distribution, the probability of one exact value is 0. That sounds strange, because exact values do occur. But any single point has 0 width, so it has 0 area under the curve. The probability becomes meaningful when we give the measurement an interval, such as between 200 and 201 milliseconds, or when a device rounds values into bins. The model predicts ranges. The recorded number represents a tiny range created by measurement precision. So, what is a normal distribution? It is a symmetric probability model with one center, mu, and one scale of spread, sigma. Area represents probability. Standard deviations provide a common ruler, and averages of many contributions often move toward this shape. What is it not? It is not a rule that all data must follow. It is not a label for healthy or ordinary people. It does not make outliers impossible, and it does not assign probability by height alone. The best habit is simple. First look at the data, then ask whether the normal curve is a useful approximation. A model earns trust by clarifying reality, not by replacing it.